Imagine a realm where the laws of physics bend and twist, where stars emerge from chaos, and celestial bodies perform intricate dances in mysterious orbits. Our universe is teeming with remarkable anomalies that defy understanding and ignite our curiosity. From the enigmatic behaviors of black holes to the elusive whispers of dark matter, these cosmic phenomena challenge us to rethink everything we believe we know. Join us as we embark on a journey to uncover some of the most captivating mysteries of space. The cosmos is a vast and enigmatic expanse filled with phenomena that challenge our understanding of physics, space, and time. Among the most compelling mysteries are black holes, dark matter, dark energy, fast radio bursts, gamma-ray bursts, and anomalies in the cosmic microwave background such as the cold spot. These phenomena not only intrigue scientists, but also drive the evolution of modern astrophysics, pushing the boundaries of human knowledge. At the heart of this mystery are black holes, regions in space where the gravitational pull is so intense that nothing, not even light, can escape. Black holes are formed when massive stars collapse under their own gravity, compressing their mass into an infinitely small point known as a singularity. At this point, the laws of physics as we understand them cease to function. This breakdown in our models challenges the core of both general relativity and quantum mechanics. Near the event horizon, the boundary around a black hole, gravity is so strong that time appears to slow down, a phenomenon predicted by Albert Einstein's theory of relativity. This effect, called time dilation, has profound implications for our understanding of spacetime. For an outside observer, an object approaching the event horizon would appear to freeze in time, an observation that aligns with the predictions of relativity. Yet, for the object itself, time flows normally. The study of black holes is not merely theoretical. Observations such as the Event Horizon Telescope's capture of the M87 black hole image in 2019 provide real-world evidence of their existence. Parallel to the study of black holes, the quest to understand dark matter represents one of the most persistent puzzles in astrophysics. First hypothesized in the 1930s by Fritz Zwicky, dark matter is an unseen form of matter that does not emit, absorb, or reflect light. It is inferred through its gravitational effects on visible matter, such as stars and galaxies. Observations of galactic rotation curves reveal that stars on the outskirts of galaxies orbit much faster than predicted by the visible mass alone. This discrepancy implies the presence of an unseen mass, which astronomers have termed dark matter. Estimated to make up about 27% of the universe's mass-energy content, dark matter acts as the scaffolding that holds galaxies together. Without it, our current models of galaxy formation and structure would fail. Despite decades of research and advancements in particle physics, the nature of dark matter remains elusive, with ongoing experiments like the Large Hadron Collider and the Xenon project attempting to detect it directly. Even more enigmatic is dark energy, a mysterious force that drives the accelerated expansion of the universe. Identified in 1998 through observations of distant Type Ia supernovae, dark energy is thought to account for approximately 68% of the universe's total energy content. Unlike dark matter, which exerts a gravitational pull, dark energy appears to work in the opposite direction, pushing galaxies apart at an increasing rate. This discovery overturned the long-held belief that the expansion of the universe was slowing down due to gravity. The exact nature of dark energy is unknown, with theories ranging from a property of space itself to the influence of new, undiscovered physics. Its effects are evident in the cosmic microwave background and the distribution of galaxies across the universe, making it a central focus of cosmological research. Projects such as the Dark Energy Survey aim to map its influence and refine our understanding of the universe's ultimate fate. In addition to these broad cosmological forces, transient phenomena like fast radio bursts, FRBs, capture the imagination of astronomers. First detected in 2007, these millisecond-long bursts of radio waves originate from unknown sources in deep space. Their origins remain a subject of debate, with theories ranging from colliding neutron stars to magnetar activity, and even speculative ideas about extraterrestrial technology. The discovery of repeating FRBs, such as those from FRB 121102, adds another layer of complexity, as these signals defy the patterns expected from cataclysmic events. Instruments like the Canadian Hydrogen Intensity Mapping Experiment, CHIME, have dramatically increased the number of detected FRBs, providing new data to analyze. However, their precise nature and mechanisms remain an open question, showcasing the universe's capacity to surprise us. Equally intriguing are gamma-ray bursts, GRBs, the most powerful explosions since the Big Bang. Discovered in the 1960s during the deployment of military satellites, these bursts can release more energy in a few seconds than the Sun will emit in its 10 billion-year lifespan. GRBs are classified into two categories: long-duration bursts, linked to the collapse of massive stars, and short-duration bursts, associated with the merger of neutron stars. These events produce phenomena such as hypernovae and are key to understanding the formation of black holes. Despite significant advancements, questions remain about what precisely triggers these immense explosions and how they interact with their surroundings. Observations from space telescopes like NASA's Fermi Gamma Ray Space Telescope continue to shed light on these mysterious events. Lastly, anomalies in the cosmic microwave background, CMB, the faint afterglow of the Big Bang, provide a window into the early universe. Discovered in 1964 by Arno Penzias and Robert Wilson, the CMB is remarkably uniform, but it contains slight temperature fluctuations that reveal information about the universe's structure and composition. Among these fluctuations is the cold spot, an area significantly cooler than its surroundings. First identified in 2004 by the Wilkinson Microwave Anisotropy Probe, WMAP, the cold spot has sparked debate among scientists. Some hypothesize that it could be a result of a massive supervoid, a region devoid of galaxies, while others suggest it might hint at phenomena beyond the standard model of cosmology, such as interactions with other universes in a multiverse framework. These anomalies challenge our understanding of the universe's evolution and continue to inspire theoretical exploration. The mysteries of the cosmos, from black holes and dark matter to transient phenomena and anomalies in the CMB, remind us of the vast unknowns that lie beyond our current scientific grasp. Each discovery not only raises new questions but also deepens our appreciation for the complexity and beauty of the universe. These cosmic puzzles fuel humanity's enduring quest to understand the cosmos and our place within it, ensuring that the search for answers will continue for generations to come. The life cycle of stars is a profound process that defines the dynamic and evolving nature of the universe. Stars, often considered the building blocks of galaxies, undergo a transformative journey from birth to death, leaving behind legacies that shape their surroundings. This intricate cycle encompasses the formation of stars in stellar nurseries, the explosive deaths of massive stars as supernovae, and the remnants they leave behind, including neutron stars and pulsars. These celestial objects not only illuminate the night sky but also serve as laboratories for understanding the fundamental laws of physics. The story of stars begins in stellar nurseries, vast regions of gas and dust where new stars are born. These nurseries, also known as molecular clouds, are primarily composed of hydrogen, the most abundant element in the universe, along with trace amounts of helium and heavier elements. Gravity plays a pivotal role in this process. Within these cold and dense clouds, small fluctuations in density cause material to clump together. Over time, these clumps grow larger as gravity pulls in more gas and dust, forming protostars. The collapse of these clumps generates immense heat and pressure, igniting nuclear fusion in their cores. This marks the birth of a new star. The energy released during fusion counterbalances the inward pull of gravity, creating a stable star that shines brightly. However, not all stars are the same. The mass of the protostar determines its fate and properties. Low-mass stars, like our Sun, burn their hydrogen fuel slowly and can shine for billions of years. Massive stars, on the other hand, consume their fuel at a much faster rate and have shorter lifespans, often only a few million years. The formation of stars is also influenced by their environment. For example, nearby supernovae explosions can compress gas and trigger star formation, a feedback mechanism that perpetuates the life cycle of stars. Regions like the Orion Nebula, a stellar nursery located approximately 1,344 light-years from Earth, offer stunning examples of these processes, with countless young stars forming amid clouds of gas and dust. As stars age, they exhaust their nuclear fuel, leading to dramatic transformations. The death of massive stars is one of the most spectacular events in the universe, a supernova. These cataclysmic explosions occur when a star depletes its supply of nuclear fuel and can no longer support itself against gravitational collapse. The core of the star collapses, releasing an immense amount of energy that propels the outer layers into space. The explosion is so bright that it can briefly outshine entire galaxies, and the ejected material enriches the surrounding interstellar medium with heavier elements like carbon, oxygen, and iron. These elements, forged in the cores of stars, are essential for the formation of planets and life. Supernovae are not only destructive but also incredibly creative. The shock waves generated by these explosions can compress nearby gas clouds, triggering the formation of new stars. This process ensures that the cycle of star formation continues, contributing to the dynamic evolution of galaxies. The remnants of supernovae are equally fascinating. Depending on the mass of the original star, the core can collapse into a neutron star or a black hole. Neutron stars, in particular, are among the most extraordinary objects in the universe. A neutron star is the dense core left behind after a supernova. Composed almost entirely of neutrons, these stars are incredibly compact. A typical neutron star has a radius of about 10 to 20 kilometers but contains more mass than the Sun. This immense density means that a sugar cube-sized amount of neutron star material would weigh as much as a mountain on Earth. Neutron stars form under extreme gravitational pressure, which forces protons and electrons to combine into neutrons. These conditions are so intense that they push the boundaries of our understanding of physics, particularly the behavior of matter under such extreme densities. The unique properties of neutron stars make them a subject of intense scientific study. Many neutron stars spin rapidly, completing a full rotation in milliseconds to seconds. These rotating neutron stars, known as pulsars, emit beams of electromagnetic radiation from their magnetic poles. As the star rotates, these beams sweep across space. If one of these beams points toward Earth, we observe it as a periodic pulse of light or radio waves, much like the beam of a lighthouse. This regularity allows pulsars to serve as cosmic clocks, with extraordinary precision. The discovery of pulsars in 1967 by Jocelyn Bell Burnell and her advisor, Anthony Hewish, revolutionized our understanding of neutron stars and their role in the universe. Pulsars have since become invaluable tools for studying a range of phenomena. For instance, the timing of pulsar signals can be used to detect gravitational waves, ripples in spacetime predicted by Albert Einstein's theory of general relativity. In 2017, scientists observed gravitational waves from the merger of two neutron stars, an event that was also accompanied by electromagnetic signals. This marked the first time such an event was observed across multiple wavelengths, opening a new era of multi-messenger astronomy. Beyond their role as cosmic clocks, pulsars provide insights into the behavior of matter under extreme conditions. Their intense magnetic fields, which can be billions of times stronger than Earth's, influence the emission of radiation and the dynamics of their surroundings. Some pulsars, known as magnetas, exhibit even more extreme magnetic fields. These magnetic fields can distort the structure of the star and produce powerful bursts of X-rays and gamma rays, offering a unique window into the physics of highly magnetized environments. The life cycle of stars is a fundamental narrative that reflects the dynamic and ever-changing nature of the universe. Stars are not simply objects that exist in isolation, but active participants in the broader cosmic tapestry. They are born, live, and die, with each stage in their life cycle having profound implications not only for the stars themselves but also for the entire universe. Their creation in stellar nurseries, their evolution through various stages of life, their eventual death in spectacular explosions, and the remnants they leave behind all contribute to shaping the universe and influencing the formation of other celestial objects, including planets and, ultimately, life itself. Stars begin their journey in the dense, cold clouds of gas and dust known as molecular clouds, or stellar nurseries. These clouds are composed primarily of hydrogen, the most abundant element in the universe. Within these clouds, regions of higher density form, and under the influence of gravity, the gas and dust begin to collapse in on themselves. This process is known as gravitational collapse. As the gas and dust fall inward, they heat up, and the central core of the collapsing mass becomes extremely hot and dense. When temperatures reach a critical threshold, nuclear fusion begins. This marks the birth of a star. In this process, hydrogen atoms are fused together to form helium, releasing vast amounts of energy in the form of light and heat. This energy counters the gravitational forces trying to compress the star further, creating an equilibrium that allows the star to shine for millions or even billions of years. Once nuclear fusion begins, the star enters the main sequence phase of its life cycle. During this period, the star is in a stable state, steadily fusing hydrogen into helium in its core. The exact length of time a star spends in the main sequence depends on its mass. More massive stars burn through their hydrogen fuel much faster than smaller stars, and therefore have shorter lifespans. The Sun, for example, is expected to remain in the main sequence for about 10 billion years, of which about 4.6 billion years have already passed. In contrast, much more massive stars might only remain in this phase for a few million years before running out of fuel. As a star depletes its hydrogen supply, the nuclear fusion process in the core begins to slow down. Without the outward pressure generated by fusion, the core contracts under the force of gravity, causing it to heat up. This process triggers the fusion of heavier elements such as helium, carbon, and oxygen in the core. As the core contracts and heats up, the outer layers of the star expand, and the star enters the red giant phase. During this stage, the star becomes many times larger than it was during the main sequence, and its outer layers cool, giving it a red color. For stars like the Sun, this phase will last for several 100 million years. In the case of massive stars, the transition to the red supergiant phase occurs, and the star grows even larger, with temperatures and pressures increasing dramatically. At the end of the red giant or red supergiant phase, a star's life takes one of two possible paths, depending on its mass. For stars with a mass less than about 8 times that of the Sun, the core becomes increasingly dense and composed mostly of carbon and oxygen. These stars shed their outer layers in powerful solar winds, creating a planetary nebula. The exposed core, now a white dwarf, continues to cool and fade over billions of years. A white dwarf is a small, incredibly dense remnant of the star's core, no longer undergoing fusion. Over time, the white dwarf will radiate away its remaining heat, and eventually become a cold, dark object known as a black dwarf, though this process takes longer than the current age of the universe. On the other hand, for massive stars, the fate is far more dramatic. When the core of a massive star runs out of fuel, it can no longer support itself against the force of gravity, and it collapses inward, leading to an extremely violent and catastrophic event known as a supernova. A supernova is one of the most energetic events in the universe, releasing vast amounts of energy and matter into space. The outer layers of the star are ejected in a spectacular explosion, while the core, if massive enough, may collapse into an extremely dense object known as a neutron star. Neutron stars are incredibly small, often only about 20 kilometers in diameter, but they are so dense that a single teaspoon of neutron star material would weigh as much as several billion tons on Earth. In some cases, if the core is massive enough, it can collapse further to form a black hole, an object with such a strong gravitational pull that not even light can escape it. The explosion of a supernova also plays a crucial role in the creation of the elements that make up the universe. The high temperatures and pressures in the core of a supernova allow for the fusion of even heavier elements such as iron, nickel, and many others. These elements are then scattered into space, enriching the interstellar medium with the building blocks necessary for the formation of new stars, planets, and even life. Without the elements created in the cores of stars and spread throughout the universe by supernovae, life as we know it would not exist. The iron in our blood, the carbon in our bodies, and the oxygen we breathe all originated in the hearts of stars. As stars live and die, they are involved in a continuous cycle of birth, death, and rebirth. The remnants of dying stars, such as the gas and dust expelled during a supernova, contribute to the formation of new stars. These remnants, along with the interstellar medium, serve as the raw materials for future generations of stars and planets. Over billions of years, this process of star birth and death shapes the structure and evolution of the universe. It is a never-ending cycle, with each generation of stars contributing to the creation of the next. The study of stars is not just a scientific endeavor, but also an exploration of the fundamental processes that govern the universe. Understanding the life cycle of stars allows us to gain insight into the larger workings of the cosmos, including the origins of galaxies, the formation of planetary systems, and the conditions necessary for life. The light from distant stars, traveling across vast stretches of space, carries with it information about the history of the universe and the processes that have shaped it. By studying this light, astronomers can learn about the age, composition, and evolution of stars, as well as the environments in which they form and die. Stars also serve as cosmic laboratories, providing us with a unique opportunity to study the fundamental laws of physics in extreme conditions. The intense heat and pressure in the cores of stars allow for nuclear reactions that we cannot replicate on Earth. The study of these reactions helps us understand the nature of matter, energy, and the forces that govern the universe. In addition, the phenomena associated with dying stars, such as supernovae, neutron stars, and black holes, offer important clues about the nature of gravity, space-time, and the fundamental nature of the universe itself. Moreover, the life cycle of stars is deeply intertwined with the broader story of the universe. Stars are the engines that drive the evolution of galaxies, creating the elements that form the building blocks of planets and life. The elements produced in stars are scattered across the cosmos, providing the raw materials for the formation of new worlds. This process of cosmic recycling highlights the interconnectedness of all things in the universe, from the birth of stars to the formation of planets, and even to the emergence of life. The death of stars is not the end of their story, but rather the beginning of something new, as their remnants give rise to new generations of stars, planets, and life forms. The life cycle of stars also has profound implications for our understanding of the universe. The processes that govern the birth, life, and death of stars have shaped the universe over billions of years, and they will continue to do so for billions more. As we continue to study stars and their life cycles, we gain a deeper appreciation for the vast, interconnected web of cosmic processes that have shaped the universe and our place within it. Stars remind us that the universe is not a static, unchanging place, but a dynamic and ever-evolving system, driven by the forces of gravity, nuclear fusion, and the fundamental laws of physics. The life cycle of stars is a continuous, interconnected process that plays a central role in shaping the universe. From their birth in stellar nurseries to their death in supernovae, and the exotic remnants they leave behind, stars are the building blocks of the cosmos. They create the elements necessary for the formation of planets and life, and they contribute to the ongoing cycle of cosmic birth, death, and rebirth. By studying the life cycle of stars, we gain a deeper understanding of the universe and our place within it, and we are reminded of the awe-inspiring forces that govern the cosmos. The universe is a grand stage where galaxies, the building blocks of the cosmos, showcase a diverse range of phenomena that continually intrigue astronomers. From the intricate structures of spiral galaxies to the enigmatic effects of gravitational lensing and the dramatic interplay of galactic collisions, these phenomena reveal the dynamic and interconnected nature of the universe. Each event or structure tells a story of cosmic evolution, offering insights into the processes that have shaped galaxies and the universe at large. Spiral galaxies are among the most visually striking and studied galactic structures. Characterized by their graceful, spiral arms, these galaxies often contain a rich mix of stars, gas, and dust. The arms of a spiral galaxy are not static, they are dynamic, wave-like structures formed by the gravitational interactions of stars and other material. Within these arms, dense regions act as stellar nurseries where new stars are born, leading to intense regions of star formation. This is why the arms often appear bright and blue, illuminated by young, hot stars. An intriguing feature of many spiral galaxies is the presence of bar structures, elongated regions of stars and gas that extend from the central bulge and connect to the spiral arms. These barred spirals are believed to play a crucial role in the dynamics of their host galaxies. Bars act as channels that funnel gas toward the galactic center, fueling star formation and even feeding supermassive black holes that often reside in the cores of galaxies. Approximately 2/3 of known spiral galaxies, including our Milky Way, exhibit such bar structures, highlighting their prevalence and importance. Not all spiral galaxies conform to the classic shape of evenly distributed arms. Some display peculiar patterns, such as feather-like structures or ring-shaped regions that hint at complex histories of gravitational interactions. These anomalies suggest that external forces, such as close encounters with other galaxies or internal instabilities, have influenced their evolution. For example, the Hoag's object, a rare ring galaxy, challenges the traditional classifications of galactic morphology and invites further investigation into how such unusual forms arise. While spiral galaxies are iconic, the phenomenon of gravitational lensing is equally compelling, showcasing the interplay of gravity and light on a cosmic scale. Predicted by Albert Einstein's theory of general relativity in 1915, gravitational lensing occurs when a massive object, such as a galaxy or galaxy cluster, lies between an observer and a more distant source of light. The massive object's gravity bends the light from the background source, magnifying and distorting its appearance. This effect acts as a natural cosmic magnifying glass, allowing astronomers to observe galaxies and structures that would otherwise be too faint or distant to detect. One of the most famous examples of gravitational lensing is the Einstein cross, where the light from a distant quasar appears as four separate images arranged around a foreground galaxy. Such phenomena not only provide stunning visual evidence of relativity but also offer a unique tool for studying the universe. By analyzing the distorted light, scientists can infer the mass distribution of the lensing object, including the presence of dark matter, an invisible substance that exerts gravitational influence but does not emit or absorb light. The distribution of dark matter revealed through gravitational lensing has been crucial for understanding the large-scale structure of the universe. Moreover, gravitational lensing enables astronomers to probe the early universe. By magnifying distant galaxies, this phenomenon allows scientists to study their composition, structure, and formation processes. Observations of these ancient galaxies provide a glimpse into the conditions that prevailed shortly after the Big Bang, offering clues about the evolution of the cosmos over billions of years. Instruments like the Hubble Space Telescope and the James Webb Space Telescope have been pivotal in capturing these extraordinary events, bringing the distant universe into sharper focus. While gravitational lensing offers insights into the vast and far-reaching, galactic collisions reveal the dramatic and intimate interactions between galaxies. Contrary to common perception, galaxies do not collide like solid objects. Instead, their immense clouds of gas and dust interact, often triggering a cascade of star formation. These collisions are relatively common, with many galaxies, including the Milky Way, expected to experience at least one significant merger during their lifetime. For example, the Andromeda Galaxy is on a collision course with the Milky Way and is predicted to merge with it in about 4.5 billion years. When two galaxies collide, their shapes are dramatically altered. Tidal forces stretch and distort the galaxies, creating elongated streams of stars and gas known as tidal tails. These tails can extend for hundreds of thousands of light years and often serve as sites of intense star formation. Famous examples include the Antennae galaxies, whose spectacular tidal tails and vibrant star-forming regions have been extensively studied. The interplay of gas during galactic collisions often leads to bursts of star formation, known as starburst events. These bursts occur when the gravitational forces of the merging galaxies compress gas clouds, triggering the collapse of material to form new stars. The resulting starburst regions shine brightly, often outshining the combined luminosity of the colliding galaxies. Over time, the newly formed stars enrich the surrounding space with heavy elements through supernovae, contributing to the ongoing cycle of cosmic evolution. In addition to star formation, galactic collisions can also influence the central regions of galaxies, often awakening dormant supermassive black holes. As gas and dust are funneled toward the galactic centers during a merger, these black holes can become active, emitting intense radiation and forming quasars. The study of such active galactic nuclei provides valuable insights into the growth and behavior of supermassive black holes, as well as their role in shaping their host galaxies. Galactic collisions are some of the most dramatic and fascinating events in the universe, leading to the formation of unique and often mesmerizing structures. These interactions between galaxies are not random, they follow specific patterns and are governed by the laws of physics, particularly the influence of gravity. The outcomes of these collisions can result in a range of phenomena, from the creation of ring galaxies to the formation of shell galaxies. Each of these structures offers valuable insights into the complex and dynamic nature of cosmic evolution, highlighting the role of gravitational forces, dark matter, and other unseen forces in shaping the universe. One of the most visually striking outcomes of galactic collisions is the formation of ring galaxies. These galaxies often appear as bright rings with a dense core, surrounded by a halo of stars and gas. The most famous example of a ring galaxy is the Cartwheel Galaxy, which exhibits a clear ring structure. Ring galaxies typically form when a smaller galaxy passes directly through the center of a larger galaxy, disrupting its structure. This type of interaction, known as a galactic collision, compresses the gas and dust in the larger galaxy, triggering a wave of star formation that propagates outward from the center. This wave of star formation creates the distinct ring-like appearance of the galaxy. The process behind the creation of a ring galaxy is highly dynamic. When the smaller galaxy passes through the larger one, its gravitational influence disturbs the gas and stars of the larger galaxy. This disturbance triggers a shockwave that compresses the gas in certain regions, leading to intense star formation. The newly formed stars give the galaxy its bright, ring-like structure. These galaxies can also exhibit unusual characteristics, such as a high concentration of young, hot stars in the central regions of the ring, while the outer regions may contain older stars and less active gas. The resulting structure is a clear indication of the violent interactions that led to its creation. In addition to ring galaxies, galactic collisions can also give rise to shell galaxies, another peculiar structure observed in the universe. Shell galaxies are characterized by a series of concentric shells of stars and gas that appear to surround a central nucleus. These shells are not uniform but vary in density and distribution, creating a complex, layered appearance. The formation of shell galaxies is believed to occur when a larger galaxy accretes smaller galaxies in a series of mergers. As the smaller galaxies are pulled into the larger one by gravity, their stars and gas are scattered in different directions, creating the concentric shells that define these galaxies. The shells in a shell galaxy are not static but are the result of complex gravitational interactions between the stars and the galaxy's dark matter. These interactions cause the stars and gas to move in highly elliptical orbits, which can lead to the formation of the distinct shells that surround the galaxy. The number and size of the shells can vary depending on the specific characteristics of the collision, including the relative sizes of the merging galaxies and their orbital dynamics. Over time, the shells may evolve and disperse, leaving behind a more diffuse structure. However, the presence of shells serves as a record of the galaxy's violent history, and the accretion of smaller galaxies. Both ring and shell galaxies offer unique windows into the processes that govern galactic evolution. These structures are not just anomalies, they are products of the fundamental forces that shape the cosmos. Galactic collisions, such as those that lead to the formation of ring and shell galaxies, demonstrate the central role of gravity in the universe. Gravity is the force that governs the movement and interaction of all matter, and it is responsible for the formation of stars, galaxies, and even larger cosmic structures like clusters of galaxies. The gravitational pull between galaxies during a collision can lead to dramatic changes in their structure, resulting in the creation of new stars, the redistribution of gas and dust, and the eventual merging of the galaxies into a single, more massive system. Dark matter also plays a crucial role in these interactions. Although dark matter cannot be seen directly, its presence is inferred from its gravitational effects on visible matter. In the case of galactic collisions, dark matter helps shape the outcome of these events by influencing the orbits of stars and gas. The dark matter in a galaxy is distributed in a halo around the visible matter, and this halo can affect the trajectory of stars and gas during a collision. The gravitational influence of dark matter can help to stabilize the resulting structure, whether it's a ring, shell, or some other configuration. Understanding the role of dark matter in galactic collisions is an ongoing area of research, as scientists continue to explore how this mysterious substance shapes the universe. The study of galactic collisions and the peculiar structures they create provides invaluable insights into the dynamics of the universe. These interactions are not just spectacular events but represent fundamental processes that drive the evolution of galaxies. By observing and analyzing these phenomena, astronomers can learn about the conditions that lead to the formation of galaxies, the role of gravity and dark matter in shaping their structure, and the eventual fate of galaxies after collisions. For instance, as galaxies collide, they can eventually merge into larger galaxies, with the resulting system exhibiting new properties and behaviors. These mergers can also trigger new waves of star formation, leading to the creation of new generations of stars and planets. Moreover, galactic collisions are also thought to play a key role in the growth of supermassive black holes at the centers of galaxies. Supermassive black holes are believed to exist in the cores of most galaxies, including our own Milky Way. These black holes can grow in size by accreting matter from their surroundings, and galactic collisions can funnel gas and stars into the black hole, causing it to grow even larger. The presence of a supermassive black hole can have significant effects on the evolution of a galaxy, influencing the motion of stars and the distribution of gas. In some cases, the energy released by the black hole can even help regulate star formation in the surrounding galaxy. The study of galactic phenomena, including galactic collisions and the unique structures they create, is essential for understanding the larger processes that govern the universe. These events provide insight into the forces that shape galaxies and their evolution, as well as the role of dark matter and supermassive black holes in cosmic evolution. Each phenomenon, whether it's the formation of ring galaxies, shell galaxies, or other unusual structures, offers a glimpse into the underlying principles that govern the cosmos. By studying these events, we continue to uncover the intricate dynamics that shape the universe, deepening our understanding of its vast and ever-changing nature. Galactic collisions are not only spectacular cosmic events but are fundamental to the evolution of galaxies and the broader universe. They create peculiar structures like ring galaxies and shell galaxies, which offer valuable insights into the dynamic processes that govern the cosmos. These interactions are driven by gravity and dark matter, and they contribute to the ongoing evolution of galaxies, the growth of supermassive black holes, and the creation of new stars and planets. As we continue to observe and analyze these events, we gain a deeper understanding of the forces that shape the universe, further enriching our knowledge of the intricate and interconnected nature of cosmic evolution. The discovery and study of exoplanets, planets that orbit stars beyond our solar system, have revolutionized our understanding of planetary systems and the potential for life in the universe. Among these worlds are unique and extreme planets, such as lava planets, hot Jupiters, and planets devoid of atmospheres, showcasing the diverse and often hostile conditions that exist beyond our solar system. Parallel to this are rogue planets, which wander the galaxy without a parent star, challenging traditional notions of planetary formation and raising intriguing possibilities for alternative habitable environments. The quest to uncover these worlds relies on advanced techniques like spectroscopy and the transit method, which allow astronomers to detect and study planets light years away from Earth. Some of the most fascinating discoveries in recent years have been the detection of unique exoplanets with extreme characteristics. A notable example is K2-141b, often referred to as a lava planet. Located approximately 202 light-years from Earth, this exoplanet is so close to its host star that its surface temperatures exceed 2,500 degrees Celsius. At such temperatures, rock on the planet's surface vaporizes, creating an atmosphere composed of rocky materials. Winds reaching supersonic speeds redistribute this vapor, leading to a rock cycle unlike anything observed on Earth. The interplay of molten lava oceans and rocky precipitation highlights the extraordinary conditions on some exoplanets. Another striking category of exoplanets is the hot Jupiters. These are gas giants similar in size to Jupiter, but they orbit extremely close to their stars, often completing an orbit in just a few days. One famous example is WASP-12b, located 1,410 light-years away in the Auriga constellation. This planet's proximity to its star causes its atmosphere to be superheated and stretched into an elongated shape, with gases being stripped away and absorbed by the star. The intense radiation creates dazzling visual effects, but it also raises questions about the long-term survivability of such planets. Hot Jupiters challenge existing models of planetary migration, as their close orbits suggest they formed farther out in their solar systems and later moved inward. Equally intriguing are planets that lack atmospheres, such as LHS 3844b, located approximately 48.6 light-years away. This rocky exoplanet has one side permanently facing its star and the other in perpetual darkness, resulting in extreme temperature differences. Without an atmosphere to distribute heat, the day side reaches temperatures of about 770 degrees Celsius, while the night side plummets to freezing levels. The absence of an atmosphere provides a unique opportunity to study the planet's surface directly, revealing potential volcanic activity or basaltic compositions similar to those found on Earth's moon. The diversity of exoplanets has expanded our understanding of what planetary environments can exist, but the search for potentially habitable planets remains a central goal. Scientists focus on the habitable zone, the region around a star where conditions might allow liquid water to exist on a planet's surface. Identifying such planets involves advanced observational techniques, particularly the transit method and spectroscopy. The transit method detects exoplanets by monitoring the brightness of a star. When a planet passes in front of its star, it causes a slight dip in brightness. This method, pioneered by the Kepler Space Telescope, has been instrumental in identifying thousands of exoplanets. By analyzing the size and orbital period of the planet, astronomers can estimate its distance from the star and its potential for habitability. Spectroscopy, on the other hand, provides detailed insights into a planet's atmosphere. By studying the light that filters through or reflects off a planet's atmosphere during a transit, scientists can detect the presence of specific molecules, such as water vapor, oxygen, or methane. These molecules can offer clues about a planet's potential to support life. For example, the discovery of water vapor in the atmosphere of K2-18b in 2019 marked a significant milestone in exoplanet research, as it suggested the presence of liquid water under certain conditions. Such observations also help scientists understand the chemical composition and climate of these distant worlds. Beyond exoplanets that orbit stars, rogue planets represent a fascinating and mysterious category of celestial objects. These planets, also known as interstellar planets, do not orbit a star. Instead, they travel through space, untethered to any stellar system. Their origins are thought to lie in the chaotic early stages of planetary formation, where gravitational interactions or collisions eject planets from their systems. Without a parent star to provide heat and light, rogue planets are often cold and dark. However, their isolation raises intriguing possibilities for unique environments. One surprising discovery about rogue planets is that they may harbor subsurface oceans. Despite the absence of stellar heat, internal heat generated by the planet's core, due to radioactive decay or residual heat from formation, could maintain liquid water beneath a thick ice layer. This concept is similar to the subsurface oceans thought to exist on moons like Europa and Enceladus within our own solar system. The potential for liquid water on rogue planets expands the possibilities for finding life in unexpected places. The detection of rogue planets, planets that do not orbit a star and instead wander through interstellar space, is one of the most difficult and fascinating challenges in modern astronomy. Unlike typical exoplanets, which are detected by observing the gravitational pull they exert on their host stars or by the dimming of starlight as they pass in front of their star, rogue planets do not have the obvious advantage of a luminous host star to help locate them. Their lack of a star makes them inherently difficult to detect using traditional methods, and astronomers must rely on more indirect and creative techniques to uncover these elusive objects. One of the most successful methods for detecting rogue planets is gravitational microlensing. This technique exploits the unique properties of gravitational fields to temporarily magnify the light of background stars. When a rogue planet passes in front of a distant star, the gravitational field of the planet can bend and focus the light of the star, creating a brief, brightening effect that can be detected by telescopes. This event, known as a microlensing event, occurs when the gravitational field of the rogue planet acts like a lens, magnifying the light from the background star for a short period of time. This effect is temporary, lasting only a few hours or days, but it can provide valuable information about the rogue planet's mass, distance from the observer, and its motion through space. Microlensing works because of the principle of general relativity, which describes how massive objects, like planets or stars, warp the fabric of spacetime. When light passes near a massive object, the object's gravity bends the path of the light, much like how a lens bends light to focus an image. By carefully monitoring the brightness of stars in regions of space where gravitational microlensing events are more likely to occur, astronomers can detect the presence of rogue planets and measure their characteristics. One of the key advantages of microlensing is that it does not require the rogue planet to emit its own light. This is particularly useful in the case of rogue planets, which do not have the bright stars that typical exoplanets orbit. Since the rogue planet itself is not visible, astronomers can detect its presence only through the magnification of light caused by its gravitational field. This method has allowed astronomers to detect rogue planets that are otherwise invisible using traditional observational techniques, providing an entirely new way to study these mysterious objects. The Optical Gravitational Lensing Experiment, OGLE, is one of the leading observatories that have contributed to the study of rogue planets using microlensing. OGLE is a long-term survey aimed at detecting microlensing events and studying the properties of objects such as rogue planets and dark matter. By monitoring a large number of stars in the Milky Way and other galaxies, OGLE has been able to identify several potential rogue planets. The data from these observations have provided crucial insights into the population of rogue planets in the galaxy, helping to estimate how common these objects might be and how they are distributed throughout the universe. In addition to OGLE, the upcoming launch of NASA's Nancy Grace Roman Space Telescope is expected to further advance the search for rogue planets. This space-based observatory will be equipped with a powerful wide-field imaging system capable of detecting microlensing events with high sensitivity. The Roman Space Telescope is expected to build on the success of OGLE by providing a broader and more detailed view of the sky, enabling astronomers to detect even more rogue planets, and potentially identifying planets that are much farther away or located in more distant regions of the galaxy. The detection and study of rogue planets have significant implications for our understanding of planetary formation and the evolution of planetary systems. The existence of rogue planets challenges many of the traditional assumptions about how planets form. Most planetary formation models are based on the idea that planets form in the disk of gas and dust surrounding a young star. Over time, these disks condense into planets that orbit the star. However, the existence of rogue planets, which are not bound to any star, suggests that planetary formation processes may be more diverse than previously thought. It is possible that some rogue planets form in a similar manner to regular exoplanets, but are ejected from their parent star system due to gravitational interactions with other planets or nearby stars. Alternatively, rogue planets could form independently in molecular clouds, without the presence of a host star, in a process known as free-floating planet formation. In either case, the study of rogue planets forces astronomers to reconsider the assumptions underlying planetary system formation. If planets can form without a star or be ejected from their home system, this suggests that the processes that govern planet formation are more complex and varied than we have understood so far. Understanding the formation mechanisms of rogue planets could help scientists develop more comprehensive models of planetary formation that take into account the possibility of planets existing independently of stars or being ejected from their systems. Moreover, the discovery of rogue planets raises important questions about the conditions necessary for life. While rogue planets are unlikely to support life as we know it due to their lack of a central star providing warmth and energy, their study can help scientists explore the broader range of environments in which life might potentially arise. For instance, some rogue planets could retain heat generated from their formation process or from radioactive decay within their cores, creating a subsurface environment that could potentially harbor microbial life. In the absence of sunlight, these planets would rely on other forms of energy, such as geothermal energy or tidal heating from interactions with nearby objects, which could allow for the development of life in extreme and unexpected environments. The study of these extreme environments challenges traditional assumptions about habitability, and encourages scientists to think more broadly about the conditions that might support life beyond Earth. The diversity of planetary environments revealed by the discovery of rogue planets also highlights the incredible variety of possible outcomes for planetary systems. While most planets are found orbiting stars in stable, well-defined orbits, rogue planets are free to wander through space, untethered to any star. Some may travel alone, while others might interact with other objects, such as stars, brown dwarfs, or even other rogue planets. This opens up the possibility of complex and chaotic interactions that could further influence the fate of these planets. For example, rogue planets may collide with other planets or stars, or they may be captured by the gravity of a nearby star, becoming part of a new planetary system. These interactions could dramatically change the properties of the rogue planet and offer opportunities for further study and exploration. The detection and study of rogue planets are thus central to advancing our understanding of the universe and our place within it. These enigmatic objects challenge existing models of planetary formation, offer new perspectives on the potential for life in extreme environments, and provide valuable information about the vast and varied nature of the cosmos. As we continue to explore the universe, the study of rogue planets will undoubtedly play a key role in reshaping our understanding of planetary systems and the conditions that support life. Through the development of new observational techniques and the ongoing expansion of our technological capabilities, we are only beginning to scratch the surface of what these mysterious worlds can teach us about the cosmos. The solar system is a dynamic and fascinating realm filled with unique phenomena and celestial bodies that defy easy categorization. While the planets often dominate our understanding of the system, many anomalies and debates center on its less traditional inhabitants and phenomena. The controversial reclassification of Pluto, the peculiarities of Venus's atmosphere, the distant and icy regions of the Kuiper Belt and the Oort cloud, and unusual orbital patterns of objects like Sedna and Haumea all highlight the diversity and complexity of our cosmic neighborhood. One of the most enduring debates in astronomy revolves around Pluto, discovered in 1930 by Clyde Tombaugh. For much of the 20th century, Pluto was celebrated as the ninth planet of the solar system. However, this status came under scrutiny as astronomers began discovering other objects in the Kuiper Belt, a region beyond the orbit of Neptune filled with icy bodies and dwarf planets. In 2006, the International Astronomical Union, IAU, redefined the criteria for what constitutes a planet, leading to the reclassification of Pluto as a dwarf planet. This decision was based on the fact that while Pluto orbits the Sun and is spherical due to its gravity, it has not cleared its orbit of other debris, one of the new criteria for planetary status. The demotion of Pluto sparked widespread controversy and debate, both within the scientific community and the public. Proponents of its reclassification argued that the discovery of similar-sized objects like Eris, another Kuiper Belt object, necessitated a clear definition of a planet. Critics, however, contended that Pluto's unique features, such as its complex geological activity and thin atmosphere composed of nitrogen, methane, and carbon monoxide, warranted its planetary status. The New Horizons mission in 2015 provided stunning close-up images of Pluto, revealing icy mountains, vast plains, and possible subsurface oceans, reigniting calls to reconsider its classification. Regardless of its label, Pluto remains a fascinating and dynamic world, continuing to challenge our understanding of planetary science. Another anomaly within the solar system lies much closer to the Sun. Venus, often referred to as Earth's twin due to its similar size and proximity, boasts an atmosphere that is anything but similar. The surface of Venus experiences temperatures exceeding 900 degrees Fahrenheit, making it hotter than Mercury, despite being farther from the Sun. This extreme heat is due to its dense atmosphere, composed primarily of carbon dioxide and clouds of sulfuric acid, which creates a runaway greenhouse effect. Adding to the intrigue is Venus's superrotation, a phenomenon where its atmosphere rotates 60 times faster than the planet itself, completing a full rotation in just 4 Earth days despite the planet's slow axial rotation of 243 Earth days. The mechanisms driving this atmospheric behavior remain poorly understood but are thought to involve complex interactions between solar heating, atmospheric pressure, and Venus's lack of a magnetic field. In 2020, Venus captured global attention when scientists announced the detection of phosphine gas in its upper atmosphere. On Earth, phosphine is associated with biological activity, raising the tantalizing possibility of microbial life existing in the planet's harsh conditions. While subsequent studies have questioned the initial findings, suggesting alternative explanations such as volcanic activity or chemical processes, the discovery underscores the mysteries surrounding Venus and the need for further exploration. Missions like NASA's Veritas and ESA's Envision, planned for the 2030s, aim to unravel these atmospheric puzzles. Beyond Venus and Pluto, the outer reaches of the Solar System contain some of its most enigmatic regions, the Kuiper Belt and the Oort cloud. The Kuiper Belt, a donut-shaped region extending from 30 to 55 astronomical units from the Sun, is home to countless icy bodies, dwarf planets, and comets. Objects in this region, such as Haumea, Makemake, and Eris, provide a glimpse into the early Solar System, as they are composed of primordial material that has remained relatively unchanged for billions of years. Haumea, in particular, stands out due to its rapid rotation, which gives it an elongated, rugby ball-like shape. Its fast spin, completing a rotation in just 3.9 hours, likely results from a past collision, making it one of the most unusual objects in the Kuiper Belt. Farther still lies the Oort cloud, a theoretical spherical shell of icy bodies surrounding the Solar System at distances up to 100,000 astronomical units. The Oort cloud is believed to be the source of long-period comets, which can take thousands of years to complete an orbit around the Sun. While no direct observations of the Oort cloud have been made, its existence is inferred from the trajectories of these comets. Both the Kuiper Belt and the Oort cloud represent reservoirs of ancient material, offering critical clues about the formation and evolution of the Solar System. The outer reaches of our Solar System, including the Kuiper Belt and the Oort cloud, are home to a number of celestial objects with highly unusual orbits, some of which challenge traditional models of planetary motion and hint at the complexity of gravitational interactions in the farthest regions of the Solar System. Among the most fascinating of these objects are Sedna, Haumea, and other bodies that exhibit strange orbital characteristics. These irregularities not only provide insight into the past dynamics of the Solar System, but also fuel speculation about the potential existence of unseen, massive objects such as the hypothetical Planet 9. Sedna, discovered in 2003, is one of the most intriguing objects in the outer Solar System. It orbits the Sun at a distance that is far beyond that of Neptune, and its orbit is highly eccentric, meaning it follows an elongated path that brings it as far as 937 astronomical units, AU, from the Sun. To put this in context, 1 AU is the average distance between Earth and the Sun, approximately 93 million miles. Sedna's orbit is so elongated that it spends a significant portion of its time far from the Sun, in the distant reaches of the Solar System. The fact that it takes around 11,400 years to complete a single orbit around the Sun adds to the mystery of this distant world. One of the most puzzling aspects of Sedna's orbit is its extreme eccentricity, which sets it apart from other objects in the Solar System. Unlike the planets, which have relatively circular orbits, Sedna's orbit is highly elongated, with the closest point to the Sun, perihelion, being roughly 76 astronomical units and the farthest point, aphelion, reaching out to 937 astronomical units. This elongated path suggests that Sedna's orbit has been influenced by some external force, possibly the gravitational interaction with a passing star or a massive object in the outer reaches of the Solar System. This has led to speculation about the existence of a hypothetical ninth planet, often referred to as Planet 9. Some researchers believe that the gravitational pull of a large, undiscovered planet may have caused Sedna's orbit to become so eccentric. However, this idea remains speculative, and further observations and data are needed to confirm or disprove the existence of such a planet. Sedna's orbit, in particular, challenges our understanding of planetary dynamics in the outer Solar System. The traditional models of planetary motion are based on the assumption that most objects in the solar system, especially those in the outer regions, should have relatively stable, elliptical orbits. However, Sedna's highly elliptical orbit suggests that there are other factors at play, influencing the movement of objects in the distant solar system. Its unusual path has led astronomers to re-examine how planetary systems evolve over time, and to consider the possibility that interactions with distant objects or stars could play a significant role in shaping the orbits of bodies in the farthest reaches of the solar system. Haumea, another intriguing object located in the Kuiper Belt, further adds to the complexity of our understanding of the outer solar system. Haumea is unique not only because of its irregular orbit but also because of its shape. Unlike most objects in the solar system, which are spherical or roughly spherical due to the force of gravity, Haumea is elongated and shaped more like a rugby ball or an egg. This unusual shape is the result of Haumea's rapid rotation, which causes it to flatten at the poles. Haumea rotates so quickly that it completes one full rotation in just 3.9 hours, which is one of the shortest days of any known object in the solar system. Haumea's orbit is also somewhat irregular. It is inclined at an angle to the plane of the solar system, and it has a moderately eccentric orbit. These characteristics suggest that Haumea's past was likely marked by significant disruptions, possibly the result of collisions with other objects in the Kuiper Belt. The Kuiper Belt, a region of icy bodies located beyond Neptune, is home to many small objects, and the frequent gravitational interactions and collisions between these objects could have played a role in shaping Haumea's unusual characteristics. Some researchers believe that Haumea's elongated shape is the result of a past collision with another large object, which may have caused the body to spin rapidly and take on its current shape. The irregular orbits of both Sedna and Haumea highlight the complex gravitational dynamics that govern the outer solar system. While the planets in the inner solar system follow relatively stable orbits, the objects in the Kuiper Belt and Oort cloud are subject to a range of influences, including interactions with other objects, the gravitational pull of nearby stars, and the presence of dark matter or other unseen forces. These interactions can cause objects to move in unpredictable ways, creating the eccentric and inclined orbits seen in objects like Sedna and Haumea. The oddities of the solar system go beyond just the unusual orbits of objects in the outer solar system. The reclassification of Pluto as a dwarf planet, for example, reflects the evolving understanding of planetary dynamics. Pluto's eccentric orbit, which sometimes brings it closer to the Sun than Neptune, challenges the traditional notion of what constitutes a planet. The discovery of Pluto's odd orbit, as well as the presence of other similar objects in the Kuiper Belt, led to the realization that Pluto is part of a larger class of objects, which are now categorized as dwarf planets. Venus, too, presents an enigma with its atmosphere and rotational characteristics. The planet has an extremely thick atmosphere composed mainly of carbon dioxide, and surface temperatures on Venus are hot enough to melt lead, making it one of the most inhospitable places in the solar system. Despite this, Venus is often described as Earth's sister planet because of its similar size and proximity to the Sun. Venus's retrograde rotation, where it spins in the opposite direction of most planets in the solar system, also presents a mystery, suggesting that some violent event in its past may have caused it to rotate in the opposite direction. These planetary oddities, combined with the strange behavior of objects like Sedna and Haumea, illustrate the incredible diversity and complexity of our cosmic neighborhood. The Kuiper Belt and Oort cloud, the icy realms located far beyond Neptune, are home to many objects that, like Sedna and Haumea, exhibit strange and intriguing characteristics. The Kuiper Belt is populated by a variety of icy bodies, including dwarf planets, comets, and other small objects, many of which have orbits that are difficult to explain with traditional models of planetary motion. The Oort cloud, an even more distant region, is thought to be the source of long-period comets, and its objects are believed to have highly irregular orbits due to gravitational interactions with passing stars and other objects in the galaxy. The study of these oddities, from the reclassification of Pluto to the exploration of the Kuiper Belt and Oort cloud, continues to expand our understanding of the solar system. Each new discovery, whether it's a strange orbit or an unexpected planetary characteristic, challenges existing theories and raises new questions about the processes that govern planetary systems. As exploration continues, the study of these unusual objects will provide crucial insights into the formation and evolution of the solar system, and perhaps even hint at the existence of new, unknown forces at work in the far reaches of space. The oddities of the solar system, from the peculiar orbits of Sedna and Haumea to the mysterious characteristics of Venus and Pluto, serve as a reminder of the complexity and unpredictability of the cosmos. Each discovery challenges our understanding of planetary motion, forcing scientists to reconsider long-held assumptions and develop new models to explain the strange behaviors observed in these distant objects. As we continue to explore these icy realms and unravel the mysteries of the outer solar system, we gain a deeper appreciation for the intricate dynamics that shape the evolution of planetary systems. In the vastness of the universe, two enigmatic forces, dark matter and dark energy, dominate the landscape, yet remain largely invisible and poorly understood. Together, these two phenomena comprise about 95% of the universe's total mass energy content, dark matter making up roughly 27%, and dark energy around 68%. Despite their overwhelming presence, both dark matter and dark energy evade direct detection, and their exact nature continues to challenge our understanding of cosmology and physics. Their effects, however, are undeniable, as they influence the structure of galaxies, the motion of celestial bodies, and the very expansion of the universe itself. One of the most compelling pieces of evidence for the existence of dark matter comes from its gravitational influence on galaxies. In the 1930s, Fritz Zwicky first observed that galaxy clusters were not moving in a way that could be explained solely by the visible matter present. He proposed that there must be some unseen mass, later called dark matter, providing the necessary gravitational pull to hold the galaxies together. Since then, numerous observations have provided indirect evidence for dark matter through its effects on the motion of galaxies. One of the most striking manifestations of dark matter is its influence on the rotation curves of galaxies. In the 1970s, Vera Rubin and Kent Ford discovered that the outer stars in spiral galaxies, like our own Milky Way, were rotating at unexpectedly high speeds. According to Newtonian mechanics, the stars at the outer edges of a galaxy should orbit more slowly than those near the center, as the visible mass decreases with distance from the galactic core. However, observations revealed that the rotational speeds remained constant, even far from the galaxy's center. This discrepancy implied that there was more mass present than could be seen, an invisible form of mass that was exerting additional gravitational force. This mass, which does not emit, absorb, or reflect light, was dubbed dark matter. The rotational curves of galaxies are now considered one of the most significant pieces of evidence for dark matter's existence. By measuring the way galaxies rotate and applying gravitational models that incorporate the effects of unseen mass, scientists are able to estimate the amount of dark matter present. These findings have led to the realization that dark matter is a fundamental component of galaxies' structure and dynamics. It is thought to constitute the majority of a galaxy's mass, with visible matter accounting for only a small fraction. The presence of dark matter explains why galaxies don't fly apart despite their high rotational speeds. Without it, galaxies would not have enough gravitational pull to hold their stars, gas, and dust together. However, dark matter doesn't only affect galaxies. It also plays a key role in the formation and behavior of large-scale cosmic structures. The presence of dark matter is crucial for understanding the distribution of galaxies in clusters. Observations of galaxy clusters reveal that the amount of visible matter alone is insufficient to explain the gravitational binding of these massive structures. Dark matter is believed to form an invisible halo around galaxies and clusters, contributing to their gravitational well. These halos are thought to have been instrumental in the formation of the cosmic web, a vast network of galaxies connected by strands of dark matter and gas. The discovery of gravitational lensing, where the gravity of galaxy clusters bends light from background objects, has further confirmed the existence of dark matter halos, revealing their size and distribution. Beyond the influence of dark matter on galaxies and clusters, a separate and equally mysterious force, dark energy, is responsible for the accelerated expansion of the universe. The existence of dark energy was first suggested in 1998 when two independent teams of astronomers observed that distant Type Ia supernovae were not only receding from Earth but doing so at an accelerating rate. This was a surprising and puzzling discovery, as gravity was expected to slow the expansion of the universe over time. Instead, the opposite appeared to be happening. In response to this unexpected behavior, scientists proposed the existence of a repulsive force that counteracts gravity and drives the expansion, dark energy. While dark matter is invisible yet detectable through its gravitational effects, dark energy is even more elusive. Unlike matter, which has mass and attracts other matter through gravity, dark energy appears to have a repulsive effect, causing space itself to stretch and galaxies to recede from each other at increasing speeds. Estimates suggest that dark energy makes up approximately 68% of the total energy content of the universe, dominating its large-scale structure. The fact that dark energy constitutes such a vast proportion of the universe has led to questions about the fundamental nature of space and the future evolution of the cosmos. The theoretical underpinnings of dark energy are still speculative, with various models attempting to explain its origins and behavior. One popular hypothesis is that dark energy is a property of space itself, known as vacuum energy. In this view, even empty space is not truly empty but is filled with fluctuating quantum fields that exert a repulsive force. Another possibility is that dark energy represents a new kind of field, similar to the cosmological constant introduced by Albert Einstein in 1917. Einstein originally proposed the cosmological constant as a way to maintain a static universe, which he later abandoned after the discovery of cosmic expansion. Today, the cosmological constant is considered a potential explanation for dark energy, but its origin and nature remain open questions. Another possible explanation for dark energy is related to quantum mechanics, specifically the idea of a quintessence field. This theory proposes that dark energy is not constant but evolves over time, with properties that could change as the universe ages. However, these models remain speculative, and there is still much to learn about the true nature of dark energy. What is clear, however, is that dark energy plays a fundamental role in shaping the future of the universe. Dark energy and dark matter are two of the most enigmatic components of the universe, playing crucial roles in its evolution and structure, yet remaining largely invisible and mysterious. Despite their profound impact on cosmology, both phenomena remain elusive in terms of direct detection and understanding. While dark matter is believed to be responsible for the formation and behavior of galaxies, galaxy clusters, and other large-scale cosmic structures, dark energy is driving the accelerated expansion of the universe itself. Both are essential to our current understanding of the cosmos, yet they introduce fundamental questions about the nature of matter, energy, and the fate of the universe. The exploration of dark matter and dark energy is at the forefront of modern physics and cosmology, promising to reshape our understanding of the universe in profound ways. The implications of dark energy are profound. If its influence continues to dominate, it suggests that the universe will continue expanding at an ever-accelerating rate. Over time, galaxies will drift further apart, and the cosmic fabric will stretch, leaving isolated islands of galaxies with increasingly vast expanses of empty space between them. This scenario, known as the Big Freeze, predicts that the universe will eventually reach a state where stars burn out, and galaxies will no longer interact with one another. Without new stars forming, the universe would become a cold, dark, and desolate place, devoid of life or meaningful structure. In this scenario, the universe's fate is an endless expansion, leading to an eventual decline in temperature, making it an inhospitable place for any form of life as we understand it. Though this scenario is speculative, it underscores the magnitude of dark energy's effects on the cosmos. If dark energy continues to push the universe apart at an accelerating pace, it raises questions about the long-term fate of the universe. Will it eventually stretch to the point where even atoms and subatomic particles are pulled apart, leading to a big rip, where the very fabric of space-time disintegrates? Or will other forces, as yet unknown, come into play and alter the universe's expansion? These questions remain unanswered and highlight the complexity and far-reaching effects of dark energy. Despite its pervasive influence, dark energy remains one of the most puzzling phenomena in physics. Unlike dark matter, which interacts gravitationally with ordinary matter and can be indirectly detected through its effects on galaxies and clusters of galaxies, dark energy does not seem to interact in any detectable way with normal matter, except through its effect on the expansion of the universe. This has made it difficult to directly observe or measure dark energy, and its true nature remains one of the most significant unsolved mysteries in cosmology. Today, dark matter is thought to be composed of particles that do not interact electromagnetically with ordinary matter, meaning they do not emit, absorb, or scatter light. This makes dark matter invisible to telescopes that rely on detecting light across the electromagnetic spectrum. However, its presence is inferred from its gravitational effects on visible matter. For example, in galaxy clusters, dark matter helps to explain the observed distribution of galaxies and the way in which they interact gravitationally. The most widely accepted candidate for dark matter particles is the weakly interacting massive particle, WIMP, though other possibilities, such as axions or sterile neutrinos, are also under investigation. Despite its gravitational influence, dark matter is not directly detectable by current observational techniques. Scientists have built sophisticated detectors and experiments designed to capture dark matter particles, but so far, these efforts have yielded no direct detection. Nonetheless, the evidence for dark matter's existence is overwhelming, from the way galaxies rotate to the large-scale structure of the universe. Dark matter's gravitational influence also plays a critical role in the formation of galaxy clusters and the large-scale cosmic web, where its effects help explain how galaxies are distributed across vast regions of space. Both dark matter and dark energy are essential to our current understanding of the universe, yet they present significant challenges for scientists trying to unravel the mysteries of the cosmos. Dark matter, while detectable through its gravitational effects, has yet to be directly observed, and its true nature remains a mystery. Dark energy, which is responsible for the accelerated expansion of the universe, is even more elusive, as it does not interact with matter in any detectable way except through its impact on cosmic expansion. The study of both dark matter and dark energy is at the forefront of modern cosmology, with scientists using advanced telescopes, particle detectors, and computer simulations to try to probe these invisible forces. The discovery of dark energy and dark matter has profound implications not only for the future of the universe but also for our understanding of the fundamental forces that govern the cosmos. These discoveries challenge our current theories of gravity, space-time, and the laws of physics. They suggest that the universe is far more complex and mysterious than previously thought, and that there are fundamental forces at work that we are only beginning to understand. The search for answers to the questions posed by dark energy and dark matter will likely drive much of the research in cosmology and physics for the foreseeable future. The phenomena of dark energy and dark matter represent two of the most significant and perplexing aspects of the universe. While dark energy is responsible for the accelerated expansion of the universe and may eventually lead to a big freeze, dark matter influences the formation of galaxies and other large-scale structures. Despite the lack of direct detection, the evidence for both forces is overwhelming, and their study is essential for our understanding of the cosmos. As scientists continue to investigate these mysterious components of the universe, the answers to the questions surrounding dark matter and dark energy may reveal new aspects of the fundamental forces that govern the universe and change our conception of reality itself. The history of human inquiry into the cosmos is deeply intertwined with the development of tools and technologies that extend our senses beyond the Earth. From the invention of the telescope in the early 17th century to the cutting-edge capabilities of the James Webb Space Telescope, humanity has constantly pushed the boundaries of exploration and observation. Alongside advancements in particle physics, which probe the fundamental forces and particles of the universe, and the transformative applications of artificial intelligence, AI, and machine learning in data analysis, these tools have revolutionized our understanding of space. Together, they have enabled scientists to explore phenomena such as dark matter, dark energy, and the existence of exoplanets, reshaping our comprehension of the universe. The story of cosmic exploration began in 1608 when the telescope was first developed by Hans Lippershey, a Dutch optician. The transformative power of this device was realized when Galileo Galilei built his own version in 1609 and used it to study celestial objects. Galileo's observations of Jupiter's moons, the phases of Venus, and the rugged surface of the Moon provided compelling evidence against the geocentric model of the universe and supported the heliocentric theory proposed by Nicholas Copernicus. This marked the beginning of modern astronomy, as Galileo's discoveries revealed a cosmos far more complex than previously imagined. Over the centuries, telescopes have undergone dramatic improvements, transitioning from simple refracting lenses to advanced reflecting designs and, eventually, to massive observatories both on Earth and in space. One major leap came in the 20th century with the construction of large ground-based telescopes like the Mount Wilson Observatory's 100-inch telescope in 1917, which allowed Edwin Hubble to observe distant galaxies. Hubble's discovery that the universe is expanding fundamentally altered our understanding of cosmology and introduced the idea of a dynamic universe. The launch of space-based telescopes has further expanded humanity's view of the universe. The Hubble Space Telescope, launched in 1990, offered an unprecedented look at the cosmos, free from the distortions of Earth's atmosphere. Hubble's contributions include the detailed mapping of distant galaxies, the observation of exoplanet atmospheres, and the confirmation of the accelerating expansion of the universe, which led to the discovery of dark energy. Following in Hubble's footsteps, the James Webb Space Telescope, JWST, launched on December 25, 2021, represents the pinnacle of modern astronomical instrumentation. With its powerful infrared capabilities and a primary mirror over 6.5 meters wide, JWST can peer into the earliest epochs of the universe, examining galaxies that formed just a few 100 million years after the Big Bang. Its ability to analyze the chemical composition of exoplanet atmospheres is particularly groundbreaking, offering new avenues in the search for habitable worlds and extraterrestrial life. While telescopes reveal the macroscopic structure of the universe, advancements in particle physics allow scientists to probe its microscopic foundations. The search for dark matter and dark energy, which collectively account for about 95% of the universe's mass energy content, relies heavily on technologies developed for particle physics. One key tool is the Large Hadron Collider, LHC, at CERN, the world's largest and most powerful particle accelerator. The LHC smashes particles together at near light speeds, enabling scientists to study the fundamental components of matter and energy. Experiments conducted at the LHC have not only confirmed the existence of the Higgs boson, a particle crucial for understanding mass, but also provided insights into the possible nature of dark matter. Another critical advancement in particle physics is the development of highly sensitive detectors for direct dark matter detection. Experiments such as Xenon and Lux Zeppelin use liquid xenon to detect weakly interacting massive particles, WIMPs, a leading candidate for dark matter. These detectors are buried deep underground to shield them from cosmic rays and other background radiation, making them capable of identifying rare interactions between dark matter particles and ordinary matter. While definitive evidence for dark matter remains elusive, these experiments represent a frontier in scientific exploration, driven by the same curiosity that propels telescopic observations of distant galaxies. Beyond dark matter, particle physics plays a vital role in studying dark energy. Observatories like the Dark Energy Survey, DES, combine advanced imaging techniques with particle physics methodologies to map the large-scale structure of the universe. By analyzing the distribution of galaxies and measuring their redshifts, scientists can infer the influence of dark energy on cosmic expansion. The intersection of particle physics and astrophysics exemplifies how different scientific disciplines converge to tackle the universe's greatest mysteries. In recent years, the rise of artificial intelligence, AI, and machine learning, ML, has transformed the way data from telescopes and particle physics experiments is analyzed. With the increasing volume and complexity of observational data, traditional methods of analysis have become insufficient. AI and ML algorithms excel at identifying patterns in vast datasets, making them invaluable tools for discovering exoplanets, analyzing galactic structures, and even detecting gravitational waves. One of the most notable applications of AI is in the identification of exoplanets. The Kepler Space Telescope, which operated from 2009 to 2018, monitored the brightness of over 150,000 stars to detect the slight dips in light caused by transiting planets. The sheer volume of data generated by Kepler presented a challenge for astronomers. By employing machine learning algorithms, researchers were able to sift through this data more efficiently, identifying over 2,600 confirmed exoplanets and many more candidates. In 2017, an AI model developed by Google analyzed Kepler data, and discovered an exoplanet system with 8 planets orbiting the star Kepler-90, demonstrating the power of machine learning in astronomical research. AI also plays a crucial role in the analysis of spectroscopy, a technique used to study the composition of celestial objects. By examining the light spectrum emitted or absorbed by a star or planet, scientists can determine its chemical makeup, temperature, and other properties. Machine learning algorithms can process spectral data at incredible speeds, identifying subtle features that might indicate the presence of water vapor, methane, or other biosignatures in exoplanet atmospheres. These capabilities are especially important for analyzing data from the James Webb Space Telescope, which generates high-resolution spectra for a wide range of celestial targets. In addition to exoplanet research, AI and ML are revolutionizing the study of gravitational waves, ripples in spacetime caused by cataclysmic events like black hole mergers. Detected for the first time in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, gravitational waves have opened a new window into the universe. AI algorithms are now used to identify these signals amidst noisy data, enabling faster and more accurate detection of events. This has led to the discovery of dozens of gravitational wave events, providing insights into the behavior of black holes, neutron stars, and the fundamental nature of gravity. The integration of artificial intelligence, AI, into astrophysics and particle physics has already begun to revolutionize the way we explore the universe, making it possible to navigate the complexities of space, interpret vast amounts of data, and make real-time decisions that were once unthinkable. As scientific missions continue to grow in scope, ambition, and complexity, the role of AI in space exploration is becoming more pivotal. From automating processes on space missions to aiding in the analysis of the enormous amounts of data generated by telescopes and particle detectors, AI is enabling scientists to explore the universe in ways that were previously impossible. Space exploration, particularly in the realms of astrophysics and particle physics, relies on cutting-edge tools and technologies, many of which have been developed over centuries of innovation. These tools, including telescopes, particle accelerators, and now AI, have been instrumental in expanding our understanding of the universe, from the distant stars and galaxies to the fundamental building blocks of matter. Each technological leap forward has brought humanity closer to unraveling the mysteries of the cosmos, offering us new insights into the nature of reality and our place in the universe. The development of telescopes over the past few centuries is a prime example of how technological advancements have expanded our ability to observe the cosmos. The earliest telescopes, such as the ones used by Galileo in the early 17th century, were simple optical instruments, yet they enabled astronomers to make groundbreaking discoveries. Galileo's observations of the moons of Jupiter, the phases of Venus, and the rugged surface of the moon fundamentally changed our understanding of the cosmos, and our place in it. These early telescopes, while rudimentary by today's standards, laid the foundation for the sophisticated space telescopes and observatories we have today. AI can also be used to optimize the operation of telescopes, ensuring that the instruments are functioning at their peak performance. For example, AI can be employed to adjust the position of a telescope's mirrors or lenses in real time, compensating for any distortions caused by the Earth's atmosphere or other environmental factors. AI-driven systems can also make decisions about which objects to observe, based on real-time analysis of the available data, optimizing the telescope's observing schedule, and ensuring that the most interesting or important targets are prioritized. AI is being used to help automate the detection of these events. Machine learning algorithms can be trained to identify the specific signatures of rare particle interactions, helping scientists to focus their attention on the most promising data. AI is also used to improve the precision of measurements, enabling scientists to make more accurate predictions about the behavior of particles and the forces at play. For instance, AI is being used to model the behavior of subatomic particles in complex experiments, providing insights into the fundamental properties of particles like quarks and leptons, as well as the forces that govern their interactions, including the elusive dark matter and dark energy. Particle physics experiments also generate enormous amounts of data, and the ability to process this data efficiently is critical for advancing our understanding of the universe. AI's ability to analyze and make predictions based on large datasets is a game changer, enabling scientists to uncover hidden patterns and relationships that would be impossible to detect through traditional methods. The integration of AI into particle physics experiments is accelerating the pace of discovery, bringing us closer to answering some of the most fundamental questions in physics, such as the nature of dark matter, dark energy, and the ultimate fate of the universe. AI-driven robotic systems also hold great potential for the future of space exploration. As missions to distant planets, moons, and asteroids become more ambitious, the need for autonomous systems that can navigate and explore these environments without human intervention becomes increasingly important. Robotic probes and landers, equipped with AI and machine learning algorithms, could autonomously explore the surface of distant planets, moons, or asteroids, conducting scientific experiments, collecting data, and even searching for signs of life. These AI systems could analyze the environment in real time, adjusting their operations based on the conditions they encounter. For example, a future mission to Mars could involve AI-powered rovers capable of navigating the planet's surface autonomously, analyzing soil samples for signs of microbial life, and transmitting data back to Earth. These rovers could make decisions about which areas to explore, based on real-time analysis of the terrain, and even adapt their behavior if they encounter obstacles or unexpected conditions. Such autonomy would be crucial for exploring distant worlds where communication with Earth may take hours or even days, making real-time human intervention impossible. In addition to its role in space exploration, AI is also transforming the way we conduct astronomical research. The vast amounts of data generated by telescopes, particle accelerators, and other instruments require increasingly sophisticated methods for analysis. AI and machine learning techniques, such as neural networks and deep learning, are enabling scientists to extract more meaningful insights from this data, allowing them to uncover new phenomena, and make more accurate predictions. AI is also helping scientists to simulate complex cosmic processes, such as the formation of galaxies, the behavior of black holes, and the evolution of stars. By running simulations based on real-world data, AI is helping us understand how the universe works on both large and small scales, providing new insights into the fundamental forces that govern the cosmos. The integration of AI into astrophysics and particle physics is just the beginning of a new era in space exploration and scientific discovery. As AI continues to evolve, its capabilities will expand, opening up new possibilities for the exploration of the universe. The tools that enable us to explore the cosmos, telescopes, particle detectors, and AI, represent the culmination of centuries of innovation, from Galileo's simple telescope to the state-of-the-art instruments of today. With each new technological leap, we gain a deeper understanding of the universe and our place in it. AI is now playing an essential role in this process, helping scientists to analyze data, optimize experiments, and make real-time decisions that will shape the future of space exploration. As the tools and technologies we use to explore the universe continue to improve, the potential for discovery remains boundless. AI and machine learning are already transforming how we study the cosmos, and as these technologies advance, they will undoubtedly lead to new insights, discoveries, and breakthroughs. Together, these innovations form a powerful arsenal for exploring the unknown, driving humanity's quest to answer the profound questions about our place in the universe. The integration of AI into astrophysics and particle physics promises to usher in a new era of space exploration, where the possibilities for discovery are limited only by our imagination and the technologies we create. The universe has fascinated humankind for millennia, not only for its vastness but for the profound mysteries it holds about its origin, structure, and destiny. Modern physics and cosmology have given rise to sophisticated theories and models that seek to answer some of the most fundamental questions about existence. Among these are the multiverse theory, which suggests the existence of multiple or even infinite universes, the cyclic universe model, which proposes an eternal cycle of creation and destruction, and the concept of parallel dimensions, which explores the existence of alternate realities and additional spatial dimensions. Each of these models challenges conventional understandings of reality, reshaping how we view time, space, and the cosmos. The multiverse theory is one of the most debated and intriguing models in cosmology. At its core, it posits that our universe is not the only one but is part of a vast ensemble of universes, collectively known as the multiverse. This idea finds its roots in three major scientific frameworks: quantum mechanics, cosmic inflation, and string theory. Each framework contributes uniquely to the multiverse concept, offering a glimpse into its potential structure and implications. In quantum mechanics, the concept of a multiverse emerges from the many worlds interpretation, proposed by Hugh Everett III in 1957. According to this interpretation, every time a quantum event occurs with multiple possible outcomes, the universe branches, creating a new, parallel universe for each outcome. For instance, when a particle's position or spin is measured, all possible states of the particle are realized, each in a separate universe. This suggests a reality where countless versions of events coexist, creating an infinite number of alternate histories and futures. While the many worlds interpretation remains speculative, it offers a potential resolution to the paradoxes of quantum mechanics, such as the superposition of particles and wave function collapse. Cosmic inflation provides another pathway to the multiverse. Developed by Alan Guth in the early 1980s, inflation theory describes a rapid exponential expansion of space in the first fractions of a second after the Big Bang. According to this model, inflationary expansion may not have stopped everywhere simultaneously, resulting in bubbles of space where inflation ceased while continuing in others. Each bubble could represent a separate universe with its own physical laws and constants. This concept, known as the eternal inflation model, suggests that our universe is merely one bubble in a vast cosmic foam of countless other universes. The differences in physical constants across these bubbles could explain why our universe is fine-tuned for life, a concept often discussed in the context of the anthropic principle. String theory, a theoretical framework that attempts to unify all fundamental forces of nature, adds another layer to the multiverse concept. In string theory, the basic building blocks of the universe are not point-like particles but tiny, vibrating strings. The way these strings vibrate determines the properties of particles, such as mass and charge. String theory also predicts the existence of extra dimensions beyond the familiar 3 dimensions of space and 1 of time. Some versions of string theory, particularly M-theory, suggest that these extra dimensions could give rise to different pocket universes, each with unique physical laws. These universes may exist within a higher dimensional space, often referred to as the bulk, which serves as a cosmic framework for the multiverse. While the multiverse theory is captivating, it also raises profound philosophical and scientific questions. If multiple universes exist, what defines their boundaries, and how do they interact, if at all? Moreover, the multiverse introduces challenges to the concept of scientific testability, as evidence for other universes may be inaccessible from within our own. Despite these challenges, the multiverse remains a fertile ground for theoretical exploration, inspiring scientists and philosophers alike to rethink the nature of reality. The cyclic universe model offers an entirely different perspective on cosmology. Unlike the multiverse, which proposes a multitude of universes existing simultaneously, the cyclic model envisions a single universe undergoing an eternal series of expansions and contractions. This idea challenges the traditional view of a singular Big Bang followed by perpetual expansion, suggesting instead that the universe has no true beginning or end. Each cycle begins with a Big Bang, followed by a phase of expansion, stabilization, and eventual collapse into a big crunch, which then triggers the next cycle. The cyclic universe model has its origins in ancient philosophical ideas but has been reinvigorated by modern physics. One of the most prominent contemporary versions is the ekpyrotic model, developed by Paul Steinhardt and Neil Turok. This model draws on concepts from string theory, proposing that our universe is a 3-dimensional brane floating within a higher dimensional space. Periodic collisions between our brane and another parallel brane create the conditions for a new Big Bang, initiating each cosmic cycle. In this framework, the cycles can stretch over trillions of years, with each iteration resetting the stage for the emergence of new stars, galaxies, and possibly life. One of the most intriguing implications of the cyclic universe model is its treatment of time. In a linear universe, time begins with the Big Bang and flows forward indefinitely. In a cyclic universe, time becomes a recurring loop, raising questions about the nature of causality and whether events in one cycle can influence those in the next. Some versions of the model even suggest that remnants of previous cycles, such as certain patterns in the cosmic microwave background, CMB, could be observable in our current universe, providing a potential way to test the theory. While the cyclic model offers elegant solutions to some cosmological puzzles, it also faces significant challenges. For example, the second law of thermodynamics, which states that entropy, or disorder, must increase over time, seems to conflict with the idea of a universe that resets itself indefinitely. Proponents of the cyclic model argue that mechanisms like entropy dilution during the collapse phase could resolve this issue, but these ideas remain speculative. Nonetheless, the cyclic universe presents a compelling alternative to the standard cosmological model, offering a vision of a cosmos that is dynamic and eternal. The concept of parallel dimensions adds another layer of complexity to our understanding of the universe. Unlike the multiverse, which posits separate and distinct universes, parallel dimensions suggest the existence of additional spatial or temporal realms that coexist with our own but are inaccessible under normal circumstances. These dimensions are a central feature of string theory, which predicts that the universe consists of up to 11 dimensions, most of which are compactified or curled up at scales too small to observe directly. The idea of parallel dimensions also appears in the brane world scenario, a subset of string theory. In this model, our three-dimensional universe is embedded in a higher dimensional space, with other branes representing parallel dimensions. Interactions between these branes could explain certain phenomena, such as gravity's relative weakness compared to other forces. In fact, some theories suggest that gravity leaks into extra dimensions, which could account for its observed behavior at both cosmic and quantum scales. Parallel dimensions are not only a feature of theoretical physics but also play a role in speculative ideas about alternate realities. These concepts have been popularized in science fiction, but also have a basis in certain interpretations of quantum mechanics. For example, the many worlds interpretation implies that every decision or quantum event creates a branching reality, effectively generating parallel dimensions where different outcomes occur. While these ideas remain unproven, they offer intriguing possibilities for understanding the fabric of existence. Exploring the implications of parallel dimensions leads to profound questions about the nature of space, time, and consciousness. Could alternate versions of ourselves exist in these dimensions? If so, what separates these realms, and is it possible to traverse them? While these questions are largely speculative, they challenge the boundaries of scientific inquiry, pushing researchers to develop new methods and tools to explore the unknown. The multiverse theory, cyclic universe model, and parallel dimensions are among the most fascinating concepts in modern cosmology. These theories push the boundaries of our understanding, offering bold and often perplexing alternatives to the conventional view of a single, linear, and finite universe. They delve into the nature of existence, time, and space, proposing scenarios where reality itself could be far more complex than we currently comprehend. While still speculative and theoretical, these ideas are rooted in advanced physics and cosmological observations, presenting profound implications for how we perceive the universe and our role within it. The multiverse theory is one of the most prominent and debated ideas in cosmology. It proposes that our universe is just one of an almost infinite number of universes that exist as part of a larger multiverse. This theory emerges naturally from certain interpretations of quantum mechanics and string theory. For example, the concept of quantum superposition, where particles exist in multiple states simultaneously, suggests the possibility of multiple outcomes occurring at the same time, potentially giving rise to parallel universes. Similarly, string theory, which attempts to unify the forces of nature, hints at the existence of higher dimensions and multiple universes as solutions to its equations. Inflationary cosmology, particularly the eternal inflation model, provides another compelling foundation for the multiverse theory. According to this model, the rapid expansion of spacetime that occurred just after the Big Bang may not have stopped everywhere simultaneously. In some regions, inflation could continue indefinitely, creating pocket universes within the broader multiverse. These universes could have different physical constants, laws of physics, and initial conditions, making each one distinct and potentially unobservable from our own. This concept is known as the bubble multiverse. One of the most intriguing implications of the multiverse theory is its potential to explain the fine-tuning of the universe. Observations show that the constants of nature, such as the strength of gravity or the electromagnetic force, appear to be finely tuned to allow for the existence of stars, planets, and life. In a multiverse scenario, each universe could have different values for these constants, and our universe is simply one where the conditions happen to be suitable for life. This anthropic reasoning has sparked intense philosophical and scientific debate, as it shifts the focus from a unique, purposeful universe to a vast ensemble of possibilities where life exists by chance. The cyclic universe model offers an entirely different perspective on cosmic evolution. Rather than envisioning a single universe that began with the Big Bang and will end in a heat death or Big Rip, the cyclic model suggests that the universe undergoes endless cycles of expansion, contraction, and rebirth. This idea has roots in ancient philosophies and has been revitalized in modern physics through theories such as the ekpyrotic model, which is inspired by string theory and higher dimensional brane cosmology. In the cyclic model, the universe avoids the singularity of the Big Bang by proposing that the current expansion phase will eventually reverse, leading to a contraction, Big Crunch, that culminates in another Big Bang. This process could be driven by mechanisms such as dark energy or interactions between higher dimensional branes. The cyclic model challenges the traditional view of time as linear, suggesting instead that time may be infinite and repetitive, with no definitive beginning or end. One of the strengths of the cyclic universe model is its ability to address certain challenges in cosmology, such as the fine-tuning problem and the initial conditions of the universe. By proposing a perpetual cycle, it eliminates the need for a unique starting point and provides a natural explanation for the uniformity and large-scale structure of the cosmos. However, the model also faces significant challenges, particularly in explaining how entropy, the measure of disorder in a system, resets itself with each cycle. Resolving this issue remains a major hurdle for proponents of the theory. The implications of these theories are profound, reshaping our understanding of the universe and our place within it. The multiverse theory challenges the uniqueness of our universe, suggesting that what we perceive as reality may be just one small piece of a much larger puzzle. The cyclic universe model invites us to reconsider the nature of time and causality, proposing a universe that is infinite and self-renewing. Parallel dimensions open up the possibility of alternate realities and higher-order structures that could fundamentally alter our perception of space and existence. While these ideas remain largely theoretical, they are grounded in rigorous mathematical frameworks and informed by observations. Advances in technology, such as more sensitive telescopes and particle detectors, may one day provide evidence to support or refute these theories. For instance, detecting signatures of other universes in the cosmic microwave background radiation, or finding evidence of extra dimensions through particle physics experiments, could lend credibility to these concepts. The study of these groundbreaking ideas also has profound philosophical implications. They challenge traditional notions of a single, ordered universe governed by fixed laws, introducing a level of uncertainty and complexity that forces us to rethink our assumptions about reality. They also raise questions about the nature of existence, the possibility of life in other universes, and the ultimate fate of the cosmos. While these questions may never be fully answered, the pursuit of these ideas exemplifies humanity's relentless curiosity and drive to comprehend the deepest truths of existence. As our tools and technologies advance, the answers to these cosmic mysteries may one day become clearer. The development of more powerful telescopes, particle accelerators, and computational models will undoubtedly provide new insights into the nature of the universe and the validity of these theories. For now, they serve as a testament to the imaginative and exploratory spirit of science, inspiring us to look beyond the limits of our current understanding and envision new possibilities for the future. Whether or not these theories ultimately prove to be correct, they underscore the boundless potential of human thought, and its capacity to grapple with the most profound questions of existence. We'd love to hear your thoughts in the comments below. If you enjoyed this video and found it informative, please like, share, and subscribe for more fascinating content. Thank you for journeying with us here on Frontiers of Infinity.